Hi there. Today we're looking at pre-trained transformers as universal computation engines by Kevin Liu, Aditya Grover, Pieter Abil, and Igor Mordach. On a high level, this paper argues that pre-trained transformers, specifically transformers pre-trained on language modeling, are doing something called universal computation. And the way they prove it is by transfer learning these transformers to completely new domains, so not language modeling. They do things like XOR tasks or C410, so computer vision. They transfer learn these transformers to these completely new domains, and they don't just do it in a regular transfer learning way. They freeze almost all of the parameters of that transformers. Specifically, they freeze all of the attention and all of the feed-forward layers in the transformer. Therefore, they only fine-tune about 0.01% or so, or 0.1% of the parameters of the model. And they show that on these specific tasks, these frozen pre-trained transformers, as you can see right here, are competitive, if not outperforming, a transformer that is fully trained from scratch on these tasks. And it also mostly outperforms LSTMs that are fully trained from scratch on these tasks. So this is pretty interesting, and it gives rise to a number of sort of questions about what happens in these transformers. So we're going to look at what the claims are and what the evidence brought forth by this paper is about why language pre-trained transformers are universal computation engines. And yeah, I'll have some comments on my own. As always, if you do like content like this, share it out, leave a like, and tell me what you think is going on here in the comments. All right, so the abstract reads, we investigate the capability of transformer pre-trained on natural language to generalize to other modalities with minimal fine-tuning. Okay? And they say in particular, without fine-tuning of the self-attention and feed-forward layers of the residual blocks. So as you know, or as you might know, a transformer is built approximately like this. So what you have is you have input, so you have the positional embeddings, and you have the input embeddings. Now, if it is a language model, that is simply one vector for every word or word piece. If it is an image model, like in the vision transformer, in the VIT, it is you simply take the image and you make it into these patches, and then each patch, you simply unroll the patch into one long vector. So you simply unroll the pixels, and that is a patch, and that in the sequence of such patches is your input. Now, what follows is these self-attention blocks, and this is the majority of the transformer is L times the self-attention blocks. You always have a attention layer, and if you don't know what an attention layer is, I'm sure you'll find some video on YouTube that explains it. This is followed by LayerNorm. This is followed by a element-wise feed-forward layer, and it is again followed by a LayerNorm. You also have the residual connections, as you can see right here. And then all of this is followed by an output layer. And the output layer is very task specific. In language modeling, it's obviously classifying into the vocabulary, so into one of whatever the 30,000 possible continuations. In computer vision, it might be classifying into the classes of the data set. So for example, in ImageNet, you'd have 1,000 classes or 21,000, depending on which version you use. So what they're saying is they are not fine-tuning, they are freezing the multi-head attention, and they're also freezing the feed-forward layers. Now these make up like 99% of the transformer. So what they get is they get a frozen pre-trained transformers, and frozen specifically refers to these parts I marked in blue. In fact, they just keep the attention and they keep the feed-forward layers as they come out of the language pre-training. And then they train the things on different tasks. So these tasks are as follows. There's bit memory. They consider a bit memory task where the model is shown 5 bit strings, each of length 1000. Afterwards, the model is shown a masked version of one of the bit strings, where each bit is masked with probability 0.5, and the model is tasked with reproducing the original bit strings. So you give it 5 bit strings in sequence, and then you give it a 6th one that is kind of corrupted, and the model must figure out which one of these 5 it is, and then it must successfully reproduce that bit string. So if it figures out it's probably numbered, the model has to look at the overlap between the strings, and then where there's the most overlap, it needs to copy over that string, or the non-overlapping parts. So this is a fairly complicated task for a model like this that is just trained with backprop, right? There is bit XOR, where you have 2 bit strings of length 5, and you need to compute the element-wise XOR. This is a long-standing difficult task for neural networks. We know that. There is list ops, where you get a sequence like this, and you must compute the result. So it's acting a little bit like a calculator. So now it turns actually out that if you think of the bit memory, that's already pretty similar to language, right? Bit XOR, maybe not. List ops, we're going to see that these models perform fairly poorly on the list ops task. And then the last one is computer vision. So MNIST and C410 is the classic like vision transformer domain, but still they take the transformer that's pre-trained on language and simply fine-tune the positional embeddings, the input embeddings, the output layer, and the LayerNorm parameters. That's all they do. And the last one is C410 from the long-range arena, where instead of forming patches like this in the long-range arena task, you simply take every single pixel into as its own kind of, so you don't do patches anymore. You unroll pixel by pixel. That is significantly longer vector for the model to compute over. So it's going to make the task a bit more difficult, because you completely lose all localization information. And the last one is this remote homology detection. It's a task from protein folding. Okay, so how do these things do? You've already seen this here in the overview. Namely, if you train these things on these bit tasks, so bit memory or bit XOR, you can see that the frozen transformer here reaches 100%, so does the full transformer. So what that shows you, it's not necessarily which one's better, it's just that both are able to completely solve this task. While, for example, an LSTM is not. Though we have no idea here what the size of the LSTM is. I don't think they stated anywhere. So the comparison with an LSTM, it is cool to see that the LSTM doesn't get this relatively simple task, but it also might just be a function of how large the LSTM is and how much rigor goes into training one. Nevertheless, the LSTM can't solve it, and that's because the LSTM takes in a sequence as just one at a time, and it needs to sort of remember in its hidden state what the individual elements are, and it can't go back, right? The transformer can always look back. The LSTM needs to remember everything, and I think that makes it much harder to do these kind of sequence tasks. I already told you list ops, they all perform badly, but interestingly, they perform equally badly. So the full transformer here is no better than the frozen transformer, which is very interesting. If you look at MNIST and C410, actually all of the other tasks, you'll see that the frozen transformer is not worse than the full transformer. In fact, it's sometimes better. And that is going to be an interesting thing also to look at. So the whole paper is actually just ablation studies into this phenomenon, like why does this happen? And it's very cool. And the result is going to be, so the authors claim that there is something special about language pre-training that already primes the transformer to be receptive to these new tasks. Now, there are two different possibilities if you think what's happening here. Actually, let's first go to the ablations and do the discussion at the end, because once you see what is happening, you'll be able to form your own opinion. What I would like to remind you though of is that they do train these LayerNorm. They do train the LayerNorm parameters, right? So when I saw this, and they said, well, we only train the input embeddings because, of course, it's a different modality, so adjusting the input embeddings makes sense, right? And the positional embeddings maybe too. And the output layer, because we have a different task, that makes sense too. And the rest we freeze. But we also adjust the LayerNorm parameters, right? But we don't adjust the attention. My immediate thought was they probably tried doing it without the LayerNorm parameters at the beginning. They probably tried just adjusting input and output embeddings. And that probably didn't work too well. And in the ablations, you're actually going to see this. So, and there, I think this hinges on the fact, and we've seen this with transformers before. I think they're called adapter layers. So if you have your kind of transformer layers one after another, what you can do is you can build in these adapter layers that have very few parameter that are kind of compressing and uncompressing the data. And that's a way you can fine-tune the transformer. So this kind of goes in and out again in dimensionality. That is a way you can adapt. And we know that these things are very possible with transformers, that you can sort of have the transformer ready and then only adjust very few parameters to transfer learn. And I think the same is going on here. Now, what the authors sort of hint at is that in the schematically, if you have the transformer, you have the attention part, which is sort of the cross information routing part, right? And then after that, you have the feed forward part, which is element wise like this. And then you sort of have a LayerNorm part. And the LayerNorm part, what it essentially is in terms of learnable parameter, is that you take one element here, or even one channel or one layer, and this depends on the exact type of norm, but in the input signal, you have two parameters that you learn. So your output of the LayerNorm is going to be a normalized X. So this is a normalization, and you do it either over the batch or over the layer or something like this. In LayerNorm, you do it over the layer, and you have two parameters that you can learn. One is a scaling, and one is an offset. And I think, by learning these, you can adapt. And this is, I think these two things have a lot of relation to each other, even though the authors say we don't learn any of the attention. I can, by influencing this A and this B right here, and this Y then goes into the next layer of attention, I can very much influence how the attention works, right? If the Y is then in the next layer, from the Y, I construct the I construct the keys, queries, and values of this particular element, and that decides what information gets routed where, and so on. So I have very much an influence over the attention in the next layer by adjusting this A. I might not have a direct influence, like I can only, if I want to change something in an element in the key, an effect of this, because I have to change the Y as a whole, is going to be that I also change something in here, but certainly backprop will figure out some way I can make this happen. Okay, so I think this whole notion of we don't influence the attention at all, it's not as clear-cut. It's true they don't change the attention parameters. However, they are able to influence how information is routed by changing the signal itself in these LayerNorm parameters. Also, they call it zero shot. They say improves performance and compute efficiency on non-language downstream tasks. In particular, we find that such pre-training enables the frozen pre-trained transformers to generalize in zero shot to these modalities. Zero shot. I think that's a bit of an overclaim. Like, I get it, you pre-train whatever, how many few percent, like only fine-tuning 0.1% of the total number of parameters of the transformer model, and none of the self-attention parameters, I don't think it's entirely fair to call this zero shot, unless I completely have overseen and misread the paper, which of course is possible because I'm just one person reading a paper. Okay, so again, we fine-tune the output layer, the input layer, the LayerNorm parameters, and the positional embeddings. My claim is this here does most of the work. Like we already know that for example, for CNNs, we can take a randomly initialized CNN, and by just adjusting the batch norm parameters, we can already gain a non-trivial result. And I think the LayerNorm here is doing a lot of the work. Of course, the input and output layer as well. We also know that we can take like a randomly initialized neural network, and simply training an output layer can already also give us a good performance. This is all stuff they do in this paper. However, I think the LayerNorm does a lot of the crucial work here but there are still some interesting things that come out of these experiments because it's not just that. Okay, so as I said, the paper is a big piece of ablation studies. Yeah, that's what I forgot. The interesting thing, of course, is that the fully trained transformer isn't better, right? That's the interesting thing. Like if you fully train a transformer on the same tasks. And this is due, I think, and I think the paper agrees, due to the fact that we are in sort of the low data regime, at least for the things here that are like the natural data sets like MNIST or CFAR10. We don't have too many data points. So training a big transformer with all the parameters could even be counterproductive because we're just going to overfit or shoot ourselves in the foot. All right, let's go through these experiments. Can pre-trained language models transfer to different modalities? And the answer here is going to be yes, absolutely. So their base thing is like a GPT-2 model that is trained on language. And it's so interesting, right, that if you transfer it to these tasks, and you can see right here, you compare it, so these are the results from figure 1. This is just what you saw in the bar diagram again. It's pretty interesting that the frozen pre-trained transformers match the performance of the full and outperform the LSTMs on these tasks. Pretty cool. So in some tasks, you can see right here in the homology, they even outperform the fully trained transformers. The second one, what is the importance of the pre-training modality? So here, they're going to compare what if we just randomly initialize a transformer and then we freeze the same layers, but they're not trained, they're randomly initialized. Or we pre-train it on this bit memory task, so it's just this one task. Or we pre-train it on ImageNet 21K. In fact, we pre-train instead of on language, on images. Or we pre-train on languages. This FPT is pre-trained on languages. Which one is going to be the best? So this is to counter people. They're making the claim that language modeling has a specific property, that language is sort of a good task to pre-train these transformers better than other modalities. So you can't just pre-train the transformer on any old task. That's what they're saying here, that language is somehow special or the best out of these ones. So in order to demonstrate that, you can see right here, this is the language one. The randomly initialized one already kind of underperforms throughout here. So actually not that much in these things here, but you can see on MNIST or on CFAR10, it does not perform too well all across. The bit memory one obviously performs well in the bit memory task. That's what it was pre-trained on, but also it kind of sucks on the rest of these tasks. It's okay in MNIST. The performance is kind of shaky, and the vision transformer is better, but it still lags behind, except on CFAR10, because being pre-trained as a vision model might, it seems like it's okay that it performs well on image modeling. The whole point here, though, is to generalize to domains out of your pre-training thing. And on these domains, the language one is better than all the other ones. Now, the question, there are multiple questions here. I think it is a bit too early from just this paper to say that language modeling has this special property, right? What I think might also be an explanation is, for example, how difficult is your pre-training task? Now, when you look at language modeling, you can look at simply how many classes does it have. So the number of classes is, in language modeling, something like 30K, like these vocabularies are fairly large. Random, it's absolutely nothing. These bit memory tasks is, so you have 2 classes. And in the vision transformer, you have 21K classes, but you only need to apply it once per sequence, right? You only have to have one output. Whereas in language modeling, you need to output every single token is a classification. So in fact, this is not necessarily more classes, but it is, let's say, more training examples per training data point that you get, because every token is a training example, essentially. So it might not be a language thing. It might just be how hard the task is in terms of number of classes and how much training data you have available. I think there are a lot of variables that they haven't necessarily controlled for here, and it might be a bit too early to say language modeling is the task. Though what I'm completely prepared to accept is to say language modeling is a good task. In fact, it's the best task out of these ones. But I think it could be cool to research more in this direction and say, okay, can we find a better task? Can we find a task that is even more complex? And that depends on what is really going on here. So I see 2 possibilities. Possibility 1, why this even works, is to say that somehow natural signals are all somehow equal. So pre-training on language somehow makes the transformer, the attention layers, just adjust themselves to the sort of natural signals that we see around us. So when we feed in an image recognition task or any other task that kind of humans care about in the natural world, the transformer is already sort of prepared about what that could entail, like about the types of computation. And then second of all, and this is different. This is simply with enough complexity, there is simply what I'm going to say computational utility. What I mean by that is that there are when you pre-train on a task, certain types of computation are going to be important for that task. And the more complex and the bigger your model, the more sort of computational primitives you can encode into the attention layers. Now, when you encode these computational primitives, it's not necessarily, of course, it has something to do with the type of signal, but I think what could be happening is that these transformers, they prepare a lot of good features that are just useful to compute different stuff, like XOR, like remembering things, and so on. I think this could definitely be the case that in these attention layers, there are these just computational primitives encoded. And if you pre-train on a task, and the harder the task is, the more of these primitives need to be encoded. And what you do when you adjust the layers in between is simply that you recombine these primitives in a better way. But sort of all of the computational primitives are already there. I think the two are not necessarily even exclusive, and I think the paper hints at both might be playing a role right here. I don't think they say exactly the same thing, but this would also give sort of meaning to this word of computation or universal computation engine. Sort of these transformers And we might even extend that to probably any machine learning model if we could scale it up and train it correctly. Probably evolves or trains to have these computational primitives inside of it. And that's why we can adjust it with just a little bit. Now they're going to claim there is something about language pre-training later. So first of all, they say how important is the transformer architecture? And here they simply say if we take a randomly initialized transformer and compare it with a randomly initialized LSTM, we freeze the attention layers, and then we just do our frozen training. Then the transformer performs a lot better than the LSTM here in most, actually all of the tasks. However, this is a very shaky comparison, of course, because how do you fairly compare a transformer architectures with an LSTM architectures? Do you control number of parameters, number of computation, speed? I don't know. Okay, so I don't know what's fair. Next, does language pre-training improve efficiency over random initialization? The answer is yes, it converges much faster if you pre-train with language. And do the frozen attention layers attend to modality-specific tokens? So here they're just going to look at the first attention layer, and they see that the attention matrix, for example, in this bit XOR task, attends. So here are the two, this is string number 1, this is string number 2, and in the output from here, you need to compute the XOR. You can see that the attention first it's on the first one, and then it's also on the second one, right? In the output, it always looks at the corresponding position. So here you can see clearly that the attention matrix already attends to the correct things for the task, which is cool because we've never trained the attention, right? But I think that goes into my claim that, look, we are still able to influence the attention matrix even though we don't train the attention weights. We are able to influence it by training these in-between parameters. The same goes for these bit memory tasks. You can see the attention matrices are very much attuned to the task right here. Next one, does freezing the transformer prevent overfitting or underfitting? And here they train this frozen transformer, and they compare it to training a transformer that just has 3 layers. So they say, our general finding is that in contrast to their fully trained counterparts, FPT models underfit the data, which lends them to further improvements by increasing model capacity. So if you compare it to a 3-layer transformer, the 3-layer transformer does outperform the 12-layer frozen transformer. However, it does so by reaching a much higher training accuracy. So overfitting is much more of a problem if you fully train the transformer. However, if you use this frozen transformer, you're probably underfitting, as you can see right here. So you could technically scale up and gain more power with this frozen fine-tuning. Does performance scale with model size? Yes. So you can see as you increase from small to medium to large, as you increase the number of layers, the performance increases. However, the performance also increases for a randomly initialized one. So it just seems to be like the more parameters, the better. It's the same. And here is something I find interesting. Can performance be attributed simply to better statistics for initializations? Here they're going to, let's say, make the point that there is something about language model pre-training that actually makes the transformer conducive to all these tasks. And you can't just reach that by better initialization, which is more point 1 from here than point 2, because point 2 you could just reach by initializing in a better way. Like these, we could characterize these computational primitives, and we could build them in from the start, whereas natural signals, we can't characterize them. Otherwise, we wouldn't need machine learning. So what they're going to do is they're simply going to take a fully trained transformer, which they call an oracle, and then they're going to compute the mean and the standard deviation so the Gaussian from those, and then they're going to initialize this new transformer. So they're going to take the pre-trained, which they have. They're going to do default, which is the randomly initialized one. We've already seen those one as well. And then they're going to take a randomly initialized one, but not randomly with the default randomization, but randomly with the statistics they got from the oracle. So this transformer is going to be randomly initialized, but it has the same statistics as the full transformer, or as a trained transformer. So the statistics are correct. And that does not seem, it seems to help a little bit, as you can see, but it does not seem to help. In fact, here it even hurts. However, I think that's a bit of a weak experiment, and I think there is still a possibility that we could initialize these transformers much better if we could correctly capture the essence of these computational primitives that are learned by gradient descent. I think if we can capture those in a theoretically sound way, we might be able to initialize. Or if we could just, if we could find like not a natural language, but if we could find a synthetic pre-training task that is just so hard, but it completely initializes all of these computational primitives, that might still be better. And that's going to be the ultimate experiment that differentiates between option 1, natural language pre-training is somehow important because of grammar and natural signals, or option 2, what we're doing is just inputting computational primitives into these layers. Does fine-tuning self-attention and feed-forward layers further improve performance? And the answer is actually no. It degrades. You can see right here, this is worse than this. And that's because probably of overfitting. If you fine-tune the whole transformer, you're going to fall down. And now here is where it really comes in that, these tasks, they are in the low data regime. I know if you go back 5 years, that sounds ridiculous, but right now these things will overfit if you train everything. And here it comes. Which parameters of the model are important to fine-tune? And you can go look at the look at the table. It's in the appendix, but they say in particular we find orthogonal initialization. Wait, we run ablations. Here, we generally find the LayerNorm parameters to be most important. The LayerNorm parameters, right? And that sort of gives credence to the fact this is not, I think what they're doing, these LayerNorms, they carry a lot of the weight of these things right here. It's still pretty cool because there are very few parameters that you need to fine tune. And okay, now they do a bunch of more ablations, like only training the output layer, which gives non-trivial performance, but not a good enough performance. So, and for some reason, I have another set of the paper right here. But this was essentially the paper. It's very cool, and the paper is super, I think it's well written and it's easy to read, because it's like, hey, here's a phenomenon we've discovered, and now we're just going to investigate all kinds of things that explain this phenomenon. We're going to rule out some stuff, some hypotheses, and we're going to arrive at some kind of conclusion in here. And that was my 2 cents to this paper. I hope you enjoyed it. It's a bit of a shorter video, and bye-bye.